now move on to the third speakers of today's forum. It's my great pleasure to introduce Professor Linda Nazar from University of Waterloo, Canada. Professor Linda Nazar's work on lithium-sulfur chemistry has had a huge impact in our field. But today, she's going to focus on the exciting area of solid-state batteries. So Linda is going to share with us on the superionic solid electrolytes for solid-state batteries. So Linda, the floor is yours.
Thank you, Shirley, and thank you for the introduction. Can everyone see my slides? Hopefully.
Yes.
So I'd like to thank the LG for the organizing this really great event and for a really interesting talk so far. And I would like to thank all of the people in particular that have contributed to this work in my group. I'll thank them at the end as well, and also my funding agencies. So as Shirley mentioned, I'm going to be talking about solid-state batteries. And of course, there's a lot of hype about this topic. I'll try to present sort of a balance between the hype and realistic views. So going from the ion cells that Jeff Dodge has beautifully described, well, arguably, there is an interest in solid-state batteries because of the flammability of liquid electrolytes. They are limited to 4.4 volts. And I guess this is, I mean, it pretty much is one of the things that's driving solid-state cells. And another, of course, is the fact that one can achieve bipolar stacking arrangements, which immediately provide a more compact and higher energy density cell by as much as a factor of 2 to 3. And they're also ideal for next generation chemistries. It is widely thought that they will probably utilize lithium metal, and they're also ideal for, or not ideal, but they can be employed with lithium sulfur batteries in the solid state. And particularly important is that they exhibit much better low and high temperature performance because one is not limited by effectively Arrhenius kinetics. One is limited by Arrhenius kinetics, but not rather by the viscosity of the electrolyte. So this is, the field of solid state batteries got quite a lot of excitement over the last couple of years. These cells rely on optimized interfaces, and I think that Shirley Meng is going to talk about that after me. I'll touch on it briefly. So here's just for those of you who are maybe not particularly familiar with it, this is a schematic diagram of a typical the first generation solid state cell, I'll call it, where a solid electrolyte within the negative electrode and the positive electrode, shown here by the red active material, and a conductive carbon typically is added as a conductive additive at the positive and at the negative. So we have the problem of the interface. I'm going to focus more on the positive electrode, which is that it's the same thing as the triple phase boundary problem in fuel cells. One has to deliver the electrons and the lithium ions to the positive electrode material effectively simultaneously. So while we don't have the problem of the reactivity of the liquid electrolyte, achieving the simultaneous electron and ion transport at the interface is a challenge. And it's particularly a challenge because many of these materials, and we're not going to talk about those beautiful single crystals that Jeff showed, but more traditional type of NMC type materials are comprised of primary crystallites that are then aggregated into these large secondary fairly large particles. And in order to basically suppress reactions of the electrolyte with that NMC material, they have to be coated with something like lithium niobate, and I'll address that in the latter portion of the talk. So controlling the interfaces, especially at the positive electrode, is really problematic. Of course, it's problematic at the negative electrode as well. So just to highlight the concerns here, we have lack of chemical stability of typical sulfide electrolytes with the positive electrode material, and poor electrochemical stability of those sulfide electrolytes. It is widely thought that, I'll just talk about lithium, but we can't totally rule out sodium, but it's widely thought that lithium is probably going to be the negative electrode of choice, although Shirley Meng has done some really lovely work, as others have, on silicon anodes. So I'll just, but in general, one has to think about the stability with lithium metal mostly being kinetic in origin. In other words, it's sort of quasi-stable. So in principle, then one also needs to implement a artificial membrane next to the lithium metal to prevent that instability, or else to generate a passivating layer in situ that solves that problem. So if we think about what the challenges of solid-state electrolytes are, well, they are many. First of all, we need a thick composite electrode, positive electrode with a high active mass, and that means we need to achieve high ionic conductivity of the solid electrolyte. As I mentioned, we have to form a stable interface with the oxide, and that means we need low redox activity with an electronically conductive additive, and that's a bit of a problem. As for the separator, we need to achieve or find thin, low-mass membrane type materials that have good mechanical properties, ductility, achieve good dynamic pressure control, and ideally have conductivities as high as 10 to the minus 2 Siemens per centimeter. And implementing lithium metal is kind of the holy grail in these systems. It means we have to achieve uniform current density over that interface, inhibit dendrites. One might ask if glasses are the answer, and vast improvements to something such as LiPon. I mentioned the problem of chemical stability, in other words, in situ formation of a stable interface or else artificial layers. And of course, then there's really nice ideas about analyst approaches from, for example, from Samsung and QuantumScape and the possibility of silicon anodes. And then finally, these are sort of bullet points that need to be addressed. We need to have good capacity and good rate capability, along with scalability of production. Okay, so to date, there's been two main classes of materials have been explored: oxides, and these include especially the garnets and also some perovskites, and for sodium cells, things like Nasicon. These materials have good oxidation stability, good thermal stability, but they have poor processing capabilities because of their very high Young's modulus. In other words, they're very brittle. On the other hand, sulfides are relatively ductile, and these include a range of lithium metal thiophosphate phases, thiophosphate glasses, and these have Young modulus significantly lower in the region of 18 to 25, but they have poor oxidation stability and thermal stability. But it's that ease of processing that has basically made them the electrolytes of choice. And in the last few years, halides have been reduced, which are sort of a compromise. They have good oxidation stability, good thermal stability, and a moderate Young's modulus, which is in the range of the sulfides, such as Iguridite that I'll be talking about today. And I'll be highlighting these at the end of the talk. So I wanted to say at the outset that there's probably not one magic bullet here, or a silver bullet, or a lithium bullet. Probably dual solid-state electrolyte systems are going to be necessary. So if we think of trying to optimize the cell potential, we're going to probably have to be coupling something like a garnet with a lithium metal chloride as a solid electrolyte in the cathode, as the catholyte. On the other hand, if we think about lithium sulfur systems, we can probably get away with things like thiophosphates because their voltage range is appropriate for the lithium sulfur cell. But it's pretty hard to imagine any solid-state electrolyte that's really going to fit both ends of the cell, so to speak. So that's just kind of a caveat here. So in my group, we're working on a lot of different strategies to achieving a benchmark of greater than 1 millisiemens per centimeter. That's because of those, because we need that, especially at the cathode, but also for the separator. And also achieving chemical and electrochemical stability of these materials. And it's, of course, difficult to achieve all of these simultaneously. I remind you here of the equation for ion conductivity, where we worry about the number of carriers and the mobility, where the mobility is defined by a pre-factor and an activation energy. So we've looked at eliminating grain boundaries by exploring superionic lithium oxythioborosilicate glasses. We've also developed some pretty unusual new materials, including this thioborosite, which has a perovskite topology, but an Iguridite-like lithium substructure. And we've explored a lot on Iguridites. I'll be talking about these in the next couple of slides. And basically achieved ultra-ionic conductivity upwards of 10 and even 20 millisiemens per centimeter. We've also been exploring the tuning of low-cost Li3PS4 to increase the conductivity. We've explored scalable solution processing. We've discovered some really interesting effects with what we call the paddle wheel rotation of anions to lower the activation energy. And then finally, as I said, trying to develop electrochemically and electrochemically stable lithium metal halides as electrolytes. So in today's talk, I'll be talking about the role of anion dynamics in achieving higher ionic conductivities, achieving fast cell conduction pathways for mobile ions, which have activation energies lower than 0.3 electron volts. And we do this with a strategy of effectively tuning the number of carriers and or flattening the energy landscape. And then also also inherent to this is achieving disorder in the mobile ion sublattice by weakening its interaction with the framework. So we've achieved, as I mentioned, some new superionic conductors with these targets, and I'll be talking about those and their cathodic and anodic stability in solid state batteries. So I'll start off with the somewhat, I would say, intriguing concept of the role of anion dynamics in fast ion conductors. And we started this first with this sodium material, sodium ion conductor, Na11SN2PS12, that we published in JAX. And we were looking, what you see here is a picosecond snapshot of the PS4 anions in this lattice. And you see the trajectory. This is from an ab initio molecular dynamics simulation. So you see the trajectory of the sulfide as this polysulfide rotates on its position in the unit cell. And this is commensurate with the mobility or the migration of the sodium ion in the cell. So after we did that work, we then decided to extend it to some lithium-ion conductors, and that's what I'll be talking about in the next few slides. And so the question that we asked ourselves was, can we create a fast ion conductive phase of boring old Li3PS4 by turning on paddle wheel effectively at room temperature? So LPS, as we call it, is in the gamma phase. The room temperature phase is completely non-conductive. It's an extremely poor ion conductor. But at 300 degrees centigrade, it becomes a reasonably good fast ion conductor, about 1 millisiemens per centimeter. And it undergoes a transition to the beta phase. And the polyhedral motif difference between the gamma and the beta is shown here. It's not really too important. What's more important is that as it undergoes the transition from the gamma to this beta phase, there is a large change in volume, an increase. And so we learned, this is a paper we published in Matter in 2019, that one could actually basically create a lattice that's very similar to that of the beta phase by stuffing this material with lithium. And what we really did was we substituted some silicon for the phosphorus. Silicon is +4 and phosphorus is +5. We effectively have to add lithium for charge balance. And so it's that additional lithium in the lattice that increases the unit cell volume even above that of the beta phase or an even higher temperature phase of the alpha. And this is one of the main factors in turning on the so-called paddle wheel effect. So on the next slide, I'm going to show you some data from a maximum entropy method. And for those of you not familiar with it, it simply extracts the information from diffraction data without any assumptions based on models. So you take your structure factors, you apply the MEM algorithm, and you can recover structural information lost in the powdered refraction data if there's reflection overlap or your reflections are out to high reciprocal space. So what it does is it gives you nuclear densities, and it's really valuable for looking at lithium-ion conductors because lithium in neutrons has a negative scattering length. But here we've used it to explore the mobility of the anions in the lattice for atoms that have a positive scattering length. So you're looking here at basically a nuclear density map, and I've labeled the atoms in this motif, so you can see what they are, and you can see that this is the PS4 group, which is shown here in the normal crystallographic motif. And I compared this then to the beta phase at 300 degrees. This is it just before the gamma phase undergoes the transition to the beta phase. And this is a conductor, this, as I mentioned, it has a conductivity of about 1 millisiemens, whereas this is extremely poor conductor. And you can see immediately a difference is that the polyanion is rigid and completely fixed in the gamma phase, whereas in the beta phase, you see rotation of this polyanion. This is, very obvious. And it is obvious from the smearing of the sulfur density as that polyanion rotates. And so this is at 300 degrees, and it's basically a direct imaging by this technique. And if you then compare that beta phase at 300 with this lithium and silicon stuff phase at basically room temperature, you see the same rotation of these polyhedral units, these PS4 groups, which are partly substituted with silicon. And again, this is evidence from this smearing of the density. And that smeared density is shown here in sort of blue and turquoise. So what we have is a rotor phase at room temperature, or close to it. And we furthermore carried out these ab initio electrodynamic simulations to understand exactly how this works. And we can see again, this is the green tetrahedra here, or the PS4 or the SIS4 tetrahedra. And this is a 1 picosecond snapshot. You can see the sulfide ions moving through their trajectories in this framework. And just to make it a little easier, in this diagram, it's described in 2 dimensions. And so you can see the mobility of these sulfide ions whipping around on their central phosphorus or silicon tetrahedra. So what's important is that if you look at the lithium diffusion in that same picosecond time frame, shown here, the lithium migrates 4.3 angstroms along the A-axis, and it migrates about 4 angstroms along the C-axis. And that is exactly the distance of the unit cell, basically from one lithium ion to another. So it basically moves 1 lattice hop during that picosecond rotation. And there are places, position or spots in the AMID simulation in which the PS4 group does not rotate, and those points, the lithium do not migrate. They just linger at their sites. So the reason how this physical coupling actually works is that this shows the diagram of the lattice, this shows the pathways for lithium ion transport, and effectively we then blow up one of these little regions. You can see that the lithium pathway that goes from a tetrahedral to an octahedral environment is that both edges are spanned by a PS4 group. And so as this PS4 group rotates, because of anion dynamics, it actually opens up these triangular windows for transport. So when the rotation pauses, we have about an 8 angstrom window, and when it rotates, we have about a 10 angstrom window. So the short and take-home message is that anion rotation opens up this triangular bottleneck, and that is key to decreasing the activation energy. And it does so by about a factor of 30%. It depends on the exact material. So my little mini summary is hopefully that I've shown you that we can turn on the paddle wheel effect at room temperature by softening an anion interaction. I might mention that the paddle wheel effect was first seen in the 1990s for oxides such as, or I should say, sulfates and phosphates, such as Li2SO4 and Na3PO4. But it was observed at elevated temperatures of 600 and 800 Kelvin. So now we can see paddle wheel effect at close to room temperature, and the part of the reason for this is, or part of the underlying mechanism to turn on that paddle wheel effect is by increasing the cell volume. It's directly coupled to the lithium mobility because of the opening of the bottleneck window, and so now we've established a superionic conductor at room temperature. And I'll get back to paddle wheel at the very end when I talk about halides. So now I'll switch gears and discuss cooperative migration and flattening the energy landscape, this being a picture of a golf course with ideally not very deep sand traps, which is what we're trying to achieve. So one of the most well-known solid-state ion conductors is our materials based on the Iguridite structure, whose formula is shown here. And so X is variable between chlorine, bromine, and iodine. It's really only the chlorine and bromine materials that are the fast ion conductors. And this is a nice cubic structure with PS4 tetrahedra and 2 lithium-ion crystallographic sites, which are known by their Wyckoff notation as 48H and 24G. So these are mostly the 48H sites, and this little transient site in between is the 24G, but almost all of the sites are the 48H. This is almost 98% occupied. So the other thing to note here is that there's the anion sites, which we, again, Wyckoff notation, the green one and the red one if you prefer, are occupied by both sulfide ions and by the halides, and they are disordered over these 2 sites. So the sulfide, the additional sulfide in the lattice, and the halide either sit here or here. And in the case of the iodide, they're actually completely ordered, whereas in the case of the chlorine and bromine, the sulfide and the halide are completely disordered. And I might add that apparently it's been seen from NMR studies by Martin Wilkening's group that anion rotation probably contributes in these igurodites as well, but that's kind of an interesting curiosity. And the igurodites are particularly utilized these days, I think, in almost in commercial or quasi-commercial solid-state cells, because they form a quasi-stable interface with lithium metal by virtue of decomposing to a stable interphase material comprised of these 3 components. So some very nice work by Marnix Backmacher has shown that the transport in the unit cell is limited by lithium ions across these cages. So these cages sit in the 4 quadrants of the unit cell. They're called Frank-Caspar polyhedra. And the point is that the lithium ions zip around within these cages very efficiently, but they undergo a more limited intercage jump. And clearly the anion that's going to sit in this position is going to affect this jump, as will the distance between the cages, and whether or not one can introduce a little stepping stone to help that jump process occur. So I'll talk about the stepping stone first. So we use the same concept that I discussed for the Li3PS4, where we stuffed it with both lithium and silicon. And we took a different Iguridite. This is an antimony iodide Iguridite, again, virtually no conductivity. And we substituted some of the antimony +5 for silicon +4, meaning we have to balance the charge with additional lithium. And so we go from having 2 of those normal lithium sites to now having 4 lithium sites in this superionic material. One of them is by notes, but we just have a numerical assignment here, lithium-3 and lithium-4. And the point is that lithium-3 is precisely that stepping stone that we were looking for. And so its effects are really quite dramatic. The conductivity of the pristine material, the antimony iodide, is negligible, the ionic conductivity, whereas when you start to substitute lithium and silicon in that structure, the conductivity now rises dramatically by orders of magnitude, reaching values between sort of 15 and 20 millisiemens per centimeter. And the activation energy drops along with that from 0.5 to 0.2, quite dramatic. And so this stepping stone, so this shows the pictures of these little Frank-Caspar polyhedra, these little cages I was mentioning with their ionic transport around in the cages, and then the limiting hop between the cages. And so the point is, here is the stepping stone position, and we have now stuffed it because we've populated this site because we have forced lithium into the lattice. And so we go from a situation where we have sort of single ion migration and a more limited step where one line has to make a hop to the other cage, to a concerted ion migration because we've now populated a higher energy site, which is the stepping stone site. And so that overall lowers the activation energy and pushes this concerted migration process where the lithium from one cage will push the stepping stone lithium out into the next cage. And this concept of concerted ion migration has been nicely highlighted by Yifei Mo in a few of his recent publications. So this is, we think, a very, very important strategy for moving forward in these materials in general. I might just add that this material has pretty good cycling. It's not outstanding, but it's really not bad with lithium. This is symmetric cells with this Iguridite in between. And you can see that there's sort of a quasi-stable interface formed between this and lithium metal. And we're able to sustain, modest current densities of 0.6 milliamps milliamps per square centimeter for upwards of 1,000 hours. And most importantly, you can see that although impedance increases modestly up to about 30 ohms, it's pretty stable over this cycling period duration. And we still don't really understand the nature of the interface. So now I'll just switch to increasing the diffusivity by weakening the framework interaction. So I already told you about this gateway site. And so I mentioned that if we could increase the halide content, in other words, make the material halide rich, we would then populate this site with more halide, and we would now have not a really hardline customs official governing this interchange jump, but one that was a little bit easier in terms of a weaker interaction of a monovalent versus a divalent anion that sits on this site. And so we simply did that by achieving materials that are chlorine rich by fairly simple techniques. And we also increased, of course, the amount of lithium vacancy. So this is kind of the opposite to stuffing the structure. But the benefit here is really just this, the weakened interaction of the lithium ion undergoing a hop with the monovalent cation now at that site, or more of it at least. And so again, the conductivity increases quite dramatically, up to about almost 10 millisiemens per centimeter as the activation energy drops concomitant with this. And so these values are of sort of 9, and for sintered pellets, not very practical, but nonetheless, values in the order of about 10 millisiemens per centimeter are fairly similar to LGPS phases that were reported recently by Ryojo Kano and the group at Toyota. But this is a very easy material to make. And we carried out pulse field gradient NMR experiments. Well, actually, we didn't carry them out. Gillian Goward's group at McMaster University and her graduate student, David Bazek, carried them out. So David did these really elegant experiments where you push a gradient across a rotor, basically, or a material in a rotor in a solid state NMR probe. And that gradient literally pushes the lithium across the material. And so you can directly measure diffusivity in meters squared per second by this technique. And so what's shown here is the data for the pristine Iguridite, the partially chlorine substituted, and then the fully chlorine substituted material in red. And you can see the dramatic increase in diffusivity, which is also seen in this tape. So we go from 2.6 to the 10 to the minus 12 meters squared per second all the way to 11. So that's an increase of 1 order of magnitude. And you can see that this value, while it's comparable to the famous lithium germanium phosphosulfide, is the value of this halide-rich material is, again, sort of an order of magnitude higher than LGPS, or this silicon material that was reported by Bettina Lach's group. And I guess what's important is that the diffusivity increases threefold, and that exactly marries with the increase in conductivity. And so we can conclude that anion disorder, that is the sulfide halide disorder, and especially the weakened interactions between the ions in the framework, along with some extra vacancies, are what's responsible for sort of a 3.5 or almost quadrupling of the ionic conductivity. And so that then led us to think about halides more and more. And I think it's, for some of you perhaps, it's well known that a lot of sulfides do not have great interfacial stability with promising cathode materials such as the NMC class. And that is because they're electrochemically unstable and chemically unstable with NMC. This is shown by a nice paper by Gerard Ceder's group, where they look at the chemical reactivity of these materials with a variety of different lithium cobalt oxide, lithium LFP, etc. The electrochemical stability is also shown by calculations, and you can see that it's limited about 2.5, 2.7 volts. And some lovely experiments by Jürgen Janik's group have shown that when you interface these Iguridites with a typical NMC type material, what you end up with is rapid capacity fade because of interface degradation. And this is clearly shown by TOF-SIMS data that show the phosphate and sulfide-like species that are formed. You can see these fragments in the TOF-SIMS. Not to mention some polysulfide formation at oxidation under oxidative conditions. So in contrast, one can think about halides because it's also been shown by various calculations, both by Ceder and by Yifei Mo, that they would have a potential window expanding up to about 4.2 volts. And that's effectively what we see by cyclic voltammetry. And these are kind of the worst case scenarios experiments because we mix the halide with a lot of conductive carbon to see what its stability is. So you can see, we compare here Li3PS4 with a mixed metal halide that we developed. I'll talk about that in the next slide. And you can see that the onset of oxidation is pretty much where it's predicted, 4.2, 4.25 volts, whereas that of the Li3PS4 starts just at about 2.5 volts. Now, this is, as I said, the worst case scenario because we're mixing a lot of conductive carbon with a halide to sort of push it to the limit, but we can actually get to voltages higher than that. And the important thing is that now we don't need to worry about trying to place electronically insulating layers like lithium niobate on the surface. We can now use a naked cathode interface and achieve much easier processing and also better performance of these materials in solid state cells. And so that's what I'll end off my talk by describing. So we were not the first, of course, to discover this. I would say that the group at Panasonic was probably the first to report in 2018 that lithium yttrium or lithium yttrium chloride or lithium yttrium bromide with modest conductivities had some pretty interesting properties, followed by a paper of Yang Shou Horns on the erbium chloride, again, sort of modest conductivity. And my colleague at the University of Western Ontario, Andy Sun, then reported on lithium indium chloride, now with a significantly higher conductivity and above that benchmark of 1 millisiemens that I mentioned. And we followed up with a paper that described substitution of zirconium in the erbium-yttrium framework to again achieve this benchmark conductivity. And what is interesting about this substitution is that we're not simply increasing vacancy concentration or anything of the sort. We're actually making a new phase. So in the phase 1, which is no zirconium substitution, in other words, lithium yttrium chloride, we have this low conductivity and fairly high activation energy. And this is a so-called trigonal phase with this space group. And as we start to substitute zirconium into the lattice, we move into a region where we have a mixture of phase 1 and this phase 2. And then finally, in region 3, we switch to a completely different phase. And this, though it has the same space group as this other material, is completely different. And you can see that just from the diagrams that I've drawn. So this is a new structure. It is fundamentally different than the others. It is certainly lithium vacancy rich by virtue of substituting a zirconium +4 for a yttrium +3. We also introduced new lithium-ion pathways in this material, and these are nicely described in the paper. I won't get into them now, but effectively there's pathways that have a lower activation energy down to about 0.3 electron volts compared to the starting material, which has an activation energy of 0.5 electron volts. So the conductivity, as you've seen in many of the other examples, increases by almost 2 orders of magnitude with this change in structure. And what we really do by changing the structure is we introduce a tetrahedral, octahedral pathway motif with this lower activation energy. So I might add that Charlie Meng's group has reported on I guess we'd call it a sodium analog to this phase. So it's the sodium version of the zirconium substituted yttrium phase, where they have, she's working together with Xu-Ping Ong, and they've seen the effects of anion rotation for the MCl6 octahedra in this material. And this is a paper published in Nature Communications this year. And this just shows the results of their AMID calculations, where if they unrestrict the chlorine motion, you can see very high diffusivities. Where they freeze it, this is computationally, you can see quite low diffusivities. And so this ion conductor is, like the other halides, stable quite to high potential, in this case to 3.8 volts. It's chemically compatible with the oxides as in their naked form. The ionic conductivity in this case isn't quite so high, but it is higher by 2 orders of magnitude than the pure yttrium, in other words, the non-zirconium substituted phase. And so this here is attributed, this effect, this 2 orders of magnitude conductivity, is attributed to both the vacancies and the really intriguing anion rotation that I mentioned earlier in the talk. We haven't looked at this in our lithium analogs yet. So on to the subject then of building real batteries. We use a variety of different cathode materials. I'll only be talking about NMC85 today. So we build our cathodes by using either an 80-20 or 90-10 ratio of the NMC to the metal halide. We get better results with 80-20, 80% NMC, 20% halide, but we get pretty reasonable results with 90-20. And then for the solid state electrolyte, we use that highly ionically conductive Iguridite that I mentioned about 10 slides ago, this silicon doped antimony iodide, and either lithium or lithium indium as our negative electrode. So this just shows that our first data that we reported, in this case it's for erbium, but the data is basically the same for yttrium. And it compares just a lithium cobalt oxide cell in which we've mixed it with a solid electrolyte, in this case Li3PS4, or in this case the halide. And then we're using Li3PS4 as a separator in these cells with a lithium indium anode. And so you can see immediately the effect of swapping out the solid electrolyte in the cathodite from Li3PS4 to the halide is really quite dramatic in terms of the capacity that we can sustain and also the cycling that we can sustain. This just shows over 2 cycles. And this shows for this cell the onset of that oxidation of the sulfide in the cell. And on the right, you see the impedance data in the cell for the 6 charge. And we're again comparing the situation for where we have the halide in the cathode. catholyte, and we have versus that where we have the Li3PS4. So in both cases, we have LPS as a separator, but we've swapped out the Li3PS4 for the halide. And you can see that the charge transfer resistance here is reduced from about 950 ohms all the way down to 40. So that's indicative of a pretty good and clean interface. And that's really what gave us a lot of excitement in this area. So we've moved on to look at other materials. We've investigated ytterbium because obviously these materials are rather expensive. It turns out ytterbium is actually rather low cost compared even with zirconium and certainly compared with indium. And in this case, we were able to find a new trigonal phase of this material. It's new for ytterbium. It's not for erbium, but it is for the ytterbium phase. And again, as we then increase the temperature, we finally form this PNMA phase, this orthorhombic phase, which is really, really similar to the one that I described for the yttrium zirconium or the erbium zirconium. So this phase has been well known, but now we have this new trigonal phase. And while its conductivity is fairly modest, this could be used as an electrode coating material because it's still good enough for that. So this is, I'll sort of zip through this. This just shows the effects of, again, increasing or substituting these materials with zirconium. So the story is really very similar to what I showed you for erbium and yttrium, just slightly different pictures, slightly different structures, but the material that we obtain on substitution is almost identical for the erbium and the yttrium. And we see a similar decrease in activation energy and increase in conductivity. So this is all quite comforting. How do we make these materials better? So the way we make them better is developing a completely different structure, which is, to our knowledge, the first halo spinel. And it has the formula shown here. It has conductivity even that can exceed 1.5 millisiemens, and again, a low activation energy. It has the same onset of oxidation potential that most of these other halides have, so a thermodynamic window of about 4.25 or 4.3, but the kinetics actually drive a higher oxidative stability of 4.5, as I'll show you in a second. And the point here is that this spinel type motif, the spinel lattice, is ideal for conduction because we have partially occupied phase sharing and octahedral and tetrahedral diffusion pathways that are all partially occupied. And so that really lowers the defect energy, the energy needed for defect formation for ion transport. So this shows the first 70 cycles of this material cycle up to 4.5 volts. You can see we have reasonably stable cycling. We've explored this in much depth. I'll just give you a couple of highlights because I only have about 1 minute left. So this shows the data over 400 cycles of this cell. We have pretty much the standard capacity that you would see for NMC 85, even in a liquid cell. So this is the same, the liquid cell, just an ECDMC, 1 molar PF6. So we get the same capacity out of the solid state cell, excellent Coulombic efficiency, and the cell lasts for 400 cycles. And of course, the liquid electrolyte cell dies off because we're not using any fancy additive. It's really not maybe a fair comparison, but there's no additives in this cell. It's just a plain vanilla electrolyte. But you can see that the difference is really quite surprising. And well, it's not surprising, but it's promising. And we've also carried out impedance studies to try to understand the origin of this really good performance. So we take in the cells, we charge them up to 4.3 volts, and then we hold them for 30 hours, which my graduate student, Laidong Zhou, who's done this work, he calls this aging. And so we monitor the leakage current until it basically dies off to zero, and we monitor the impedance every 20 minutes. And you can see that on this 4.3 volt hold for 30 hours, the impedance changes very little. And after 30 hours, we get a charge transfer resistance, which is very low, very modest, of about 38 ohms. And if we take the cell and we keep returning it to its discharge state, as we take it up to 4.3 volts, and then look at the impedance when we return it back to discharge over 160 cycles, there is effectively no change in impedance. So what this gives is a cell then that really functions pretty well. This is at room temperature, and this is at a 3C rate because we've also done studies at 2C. This was our initial study because we wanted to get the data collected quickly. So you can see that we achieve 80% capacity retention over 3,000 cycles for this cell. And again, I repeat, this is at room temperature. And the reason that we think we see this good performance is that because we don't have to coat the NMC particles with lithium niobate, which acts as a real hindrance to both ion and electronic mobility, because a lithium niobate is not a good lithium-ion conductor at all. We now have this relatively limited case replaced with one where we have good electron transport and ion transport in the material, because effectively the particles are forced together. This coating that we form is really kind of patchy. And so it's not in a matrix of the halide. We just simply have the halide coated in patchy particles, leaving some bare spots. And so, so that facilitates both electron and ion migration in the material. I'll end off then by just letting you know that I think we keep our publication fairly up to date. So things are all described, and this work is all described in a lot of detail on our website. So I hope I've convinced you of the importance of anion dynamics by lowering the activation energy. I didn't really get into the numbers, but it's on the order of a factor of as much as 2 by this paddle wheel effect. My web is showing you some new descriptors for ultra-superionic conductivity that are necessary to sustain thick electrodes. This is with the stepping stones and concerted ion migration. And these are really critical strategies, I think, going forward to develop new solid-state electrolytes. We still need to get the halides to conductivities in the order of 10 millisiemens per centimeter to make them better electrolytes for the cathode. So this is where we're going in our group, and also, of course, to increase the voltage stability of those materials. And so ultimately, understanding and mastering the interfaces are all next steps. So with that, I would like to thank my lab group. This is a year or two ago, I guess, when we were all able to gather at a Christmas party. Hopefully we'll get back to that point soon. I'd like to thank all of these people who contributed to the work. This is for my group and also our collaborators at ONRL, Professor Goward and David Bazek at Master, and Shahan Wu at BSF, and our funding agencies. And I'd like to thank you for your attention.
Thank you, Linda. Certainly very, very exciting for the solid state sciences that you have presented today. We do have a short question for you. So in terms of the development of the solid state batteries, what is your opinion about the hybrid approach where the liquid is mixed with the solid in order to achieve certain attractive properties of the battery?
Well, I think that it's probably the first step that people need to take on this long, hard road to developing solid state batteries. So I think it's certainly a promising approach to start off with, or I mean, to really develop over the next couple of years. I don't think it'll ultimately be the solution that we're searching for, but I wouldn't say that with any degree of absolute certainty. It kind of depends on the safety aspects that these hybrid cells show.
Thank you, Linda. I think it's certainly very exciting to see that your strategies can provide a better conductivity liquid electrolyte, because you're reaching 20 millisiemens per centimeter at room temperature. So it's really quite exciting. Perhaps the liquid approach is not necessary from the conductivity perspective. So thank you very much for sharing your insight. And I think we are right on the clock. And also, I want to thank you for staying up so late. Hopefully that we can have discussions on the solid state batteries later after my presentation. So right now, I'm going to give my microphone